In this video, I want to introduce you to the last concept that we're going to be looking at this quarter, okay? And that is eigenvalues and eigenvectors. Here's the definition. If A is an n by n matrix, then a scalar lambda, you could use any constant you want, but for whatever reason we use the Greek letter lambda to do this. This is called an eigenvalue of the matrix A if there exists a non-zero vector x in Rn such that A times x equals lambda x. So if you're thinking about matrix transformation, what we're saying is that the vector x is being sent to just a scalar multiple of itself. Okay. Now, any such vector x that satisfies this equation is called an eigenvector corresponding to the eigenvalue lambda. Now, I want to point out that this definition is different from the book. The book defines eigenvector first and then eigenvalue second, and I do it the other way around. The reason I do it this way is that the book says that if A is an n by n matrix, then a non-zero vector x is an eigenvector if there exists a lambda such that this is true. Okay? So they insist that the x be not zero, not the zero vector. But then later we'll see in the subsequent video here that the set of all, if you got a particular value lambda, then the set of all eigenvectors for that lambda is a subspace of Rn. Well, if it's a subspace of Rn, you better well let the zero vector be one of them, because you've got to have zero vectors in your subspaces. So it just seems to me the way they define it, they don't allow the zero vector to be an eigenvector. And the way I do it, it does. Okay. Now, also notice here that no matter what lambda you choose, A times the zero vector is going to be lambda times the zero vector. They're both the zero vector. So essentially the zero vector is an eigenvector for any lambda. However, I would not call any lambda an eigenvalue, because in order to be an eigenvalue, you have to make it work for some non-zero vector. Yeah, it'll work for zero as well, but it's got to also work for something that's not zero. Okay, that's what makes it an eigenvalue. Here's an example. This is the matrix A. Multiplying that by this causes a reflection over the line y equals x, right? And so notice, if I take something on the line y equals x, say the vector 2, 2, that gets sent to 2, 2. Do the multiplication, you get this. But 2, 2 is 1 times 2, 2. So this vector, 2, 2, is an eigenvector corresponding to the eigenvalue 1. Right? So 1 is an eigenvalue, and here is an eigenvector. In fact, anything on the line y equals x would work in a similar way. But also notice that if I were to look at the vector minus 3, 3, which lies on the line y equals minus x, then I multiply it by this matrix, what I get is 3 minus 3, which is actually equal to minus 1 times minus 3, 3. So this vector, minus 3, 3, gets sent to minus 1 times itself, which means that minus 1 is an eigenvalue for this matrix, and negative 3, 3 is an eigenvector corresponding to that eigenvalue. As it turns out, although I'm not proving this at the moment, that those are the only two eigenvalues for this matrix, 1 and minus 1. And the eigenvectors corresponding to the first eigenvalue are all the vectors that lie along the line y equals x, and all the eigenvalues corresponding to minus 1 are the vectors that lie along the line y equals minus x. Here's another example. Dilation. So what I want to do is I want to multiply by this matrix. And notice for any vector, xy, when I multiply by 4, 0, 0, 4, I get 4x, 4y, which is 4 times xy. So 4 is an eigenvalue, and any xy, it turns out any vector you want, is an eigenvector for lambda equals 4. Right? That dilation just takes everything and makes it bigger, in this case 4 times as big, so any vector pointing in a particular direction just gets to be stretched out by a factor of 4 in that direction, and that's exactly what an eigenvalue is an eigenvector is, right? 4 is the eigenvalue, and any vector here is an eigenvector. On the other hand, take a look at rotation. I'm going to rotate through an angle of pi over 2. The matrix that does that is this one, right? Remember, it's sine theta, so cosine theta, minus sine theta, cosine theta. Well, at pi over 2, the cosines are 0, and the sine is 1. So minus the sine here is minus 1. So when I multiply by xy, I get minus yx. Now, xy is any particular vector, and minus yx is a vector that's rotated 90 degrees from it, or pi over 2. They will never be in the same direction. They will never be, the output will never be a scalar multiple of the input. Right? There isn't any way that you're going to just multiply this by a constant and get minus yx. So that matrix does not have any eigenvalues or eigenvectors. At least not real ones. If we had a second quarter, we might start looking at complex eigenvalues and things like that, but not this quarter. Here's another example. This is a very special rotation. In general, rotations don't have eigenvalues, right? That vectors here get rotated, they're not pointing in the same direction. However, there's one special rotation that if you rotate exactly pi and you end up pointing in exactly the opposite direction, then minus 1 will be an eigenvalue, right? That if I multiply by this matrix here, I get minus x minus y, and that's minus 1 times xy. So every vector is an eigenvector for the eigenvalue minus 1. In general, though, rotations don't have eigenvalues. Just this special one does. Right? And I want to point out that all the examples that I've given here are in R2, but the concept here was defined for Rn, and you can have, eigenvectors for eigenvalues for any n by n matrix. Okay. It's just that it's easiest to work with and draw pictures of in R2. Speaking of pictures, let's finish this video with a visual approach. Take a look at the matrix 1, 2, 3, 4. And what I want to do is I want to look at a vector and its image under the transformation TA and decide if I can see eigenvalues and eigenvectors. So here we go. What I have here is a vector, small unit vector here in black, and the blue vector is the vector transformed. Take the matrix 1, 2, 3, 4 and multiply it by this black vector, you get the blue one. Now, I don't know, the blue one may go off the edge of the screen here. But what I have here is a slider that allows me to manipulate the black vector. It's always going to be length 1, it's just going to point in different directions. So as I slide this around, you can see the black vector move around the unit circle. Okay, so I only really need to look at those unit vectors because I know that matrix transformations satisfy the homogeneity property. So any input that's a scalar multiple of this one will have an output that's a scalar multiple of that one. So if I know the direction of the input, I can see the direction of the output. The actual lengths I'm not particularly worried about, right? But I can move this around and I can see some things. For instance, I can see right there. That's a really interesting position because the vector, black vector, and the output, the blue vector, are pointing in the same direction. So the output is a scalar multiple of the input. This black vector is an eigenvector for this matrix, 1, 2, 3, 4, and there's clearly some positive eigenvalue. I don't know what it is because I can't really see how long that blue vector is. I believe that also happened back here somewhere. Yeah, there's one up there, but that's just the same direction or the opposite direction. It's still that same positive eigenvalue. But there was another spot of interest right about, it happens quick here, right about in there. Don't seem to get it lined up quite right, but pretty close, where the output vector is in exactly the opposite direction of the input vector. And so what I see here is that, yeah, there's a direction here that is the direction for eigenvectors with a negative eigenvalue. In fact, a negative small eigenvalue because the output is shorter than the input. So lambda is going to be somewhere between 0 and -1 for this. Okay. So, and I believe that happens over here as well, and then in the opposite direction. Yep. Getting it to land exactly is pretty tricky. But there we go. We can see that this will have two eigenvalues, one positive, one negative. One bigger than one somewhere between 0 and -1. Okay. Now the question becomes, how do we find eigenvalues? And that is the topic of the next video.